Welcome to the Model-Based Reinforcement Learning lecture. Today we'll discuss about models, how can we learn them, how can we use them to select actions and to train our policies, what are the pitfalls to, to take care of. A model concretely is the transition function and the reward function. We've seen these two functions all along in this course. Instead of assuming that the model is given, as we did when we discussed about planning and learning using Monte Carlo tree search, we're going to try to learn these two functions from experience. We have some design choices to make here. What should be our action representation? What should be the learning machinery behind this, that we're going to fit these experience tuples? We do have a very simple supervised learning problem when we learn models, so this is the that's why we like it. We can take gradients. There are not the difficulties that arise when we try to learn under specific task-related rewards. Now, the one question that comes in mind, and many people have, a particular traditional robotics researchers, is why do we need to consider general learning models as opposed to Newtonian systems of equations, where potentially few parameters are hidden. We do not know their values, but we do know the structure, right, of the parametric form. In this case, if we were using a system of Newtonian equations of motion, for example, to predict how objects move under forces of the agent, we would need to learn only very few parameters. So naturally, it would be very easy to fit and to generalize. The truth is that the real world is very complex. Not only the parameter values are unknown of the friction coefficient or the inertia matrix of the objects, but rather there are many unobserved phenomena. Maybe there is wind. Maybe the way the agent touches the object is very difficult to model using standard physics. Okay? So that's why we depart from traditional physics and we try to learn those rules of motion, and we call those models of intuitive physics, okay? Because, and an argument why the human brain may be learning intuitive physics as opposed to, fitting Newtonian systems of equations is that a very small part of the world knows about Newton, all right? Yet everybody can act so well and can predict outcomes of our actions. Now, as soon as you decide to depart from transitional physics, you have the problem that you need to fit a large number of parameters, and the question of generalization of this model is very important and is upfront. So we'll see exactly about this, how this question enters into the discussion. If you remember, in our previous lecture, we discussed how can we use learned dynamics for exploration to drive our curiosity rewards. Whenever the prediction model would make a mistake, we would give a high exploratory bonus to this particular state, okay, which our critic would learn and would guide the policy towards states that would provide such high reward, will make our prediction model to fail. There, we did have a short discussion of what should be the architecture of that transition model. We said, so this same discussion is relevant here, okay? So the first thing we can do is to predict directly raw visual observations. And now I'm talking about visual observations because I'm from computer vision. Now, if you have tactile feedback, you may just go and predict raw tactile input or raw audio input, etc. And people have done this, okay? And given its difficulty, and we have seen why it's difficult, right? It's very high dimensional observations. You would ask, why do people care so much? Well, because if you have the observation available, if you take an action and you are able to guess what will be the future observation, then from this observation, you can calculate a bunch of rewards that may come to your mind. Not only how you're going to win the game, right, which you would be able to do if you were predicting this scalar value, but rather, how can I make Mario to jump? How can I make him run backwards, forward, jump in the well, jump down, etc. Tons of related goals. And unfortunately, this does not, I'm sure this is not very easy to grasp when I show you Super Mario, okay, which the only thing that you care about is to advance forward in the game. But think, for example, about billiards. Let's say you want to play billiards. Sometimes you want to shoot the ball towards the left, sometimes towards the right. Sometimes you want to make it bounce on the wall and bounce back and then go diagonally to your target. So you need to be able to have a very, very diverse set of policies, okay? So instead of learning those policies directly, you learn a model which, once you have folded, all those rewards can be evaluated. Does this make sense? So the model knowledge is useful under a range of different goals that you might be interested to achieve. So we will see, in fact, model learning for billiards in a second. So there's nothing new here. We've seen exactly this model before. Action condition video prediction for Atari games, if you remember, right, in the previous lecture. Now, a better choice would be, instead of predicting their observations, to predict an embedding H. And the question is, so this H, the hope is going to be lower dimensional of the observation, thus easier to predict. The question is, what should H capture from the observation? Well, it should capture whatever you guys would need to predict your goals. If you care to control Mario in any way, this H should capture everything about the motion of the agent you want to control, but forget about anything that you cannot control, because it will make your prediction problem easier. How can you design such magical H? One solution we saw in the previous lecture was to couple this forward model learning with inverse model learning. Okay? So inverse model essentially says capture in this embedding of your observation only the information that will allow you to recover the action of the agent. Imagine the agent is stationary, is not acting. A lot of things are changing on the background, right? Birds are flying, monsters are jumping. All those will be neglected because you cannot use them to recover the action of the agent. All right? Now, I'm not arguing that this is the right embedding H. I may not be able to control a monster, but I would very much like to predict what's going to happen when a monster enters towards me, if that makes sense. But it's a shortcut towards finding this golden H. What can you do with this H? Well, I can give you then a target goal image, compute the target goal H, and estimate your reward based on this distance. The larger the distance, the lower your reward. Okay? Overall, this is going to be a general theme. We'll take a model, unroll it, predict, compare the prediction to our desired configuration. The larger the distance, the lower the reward. We try to change our actions so that we make the long-term predictions closer to what we care to predict, to our desired goal. So here it is again. Yes, and we can unroll. Unrolling will fast cause our model to be inaccurate. Why? Because the CNN, or your learning machine, takes as input its own predictions. Its own predictions naturally will have some certain error. Once you feed your own predictions, errors will accumulate. What people have done, and it works well, is the following. Instead of feeding a very instantaneous action, feed an action sequence and try to predict the outcome. That is, instead of very fine-grained temporal models that you need to unroll quite many times to look ahead far in the future, train coarser in time, in coarser temporal granularity models. And then you can look ahead by very few unrolls. And we'll see an example of this at the end of the lecture. Whatever I'm discussing now, we will see examples of all this in the lecture. I'm just trying to summarize the points. Yes? Yes, by unrolling I mean the following. You have a model that takes as input the state or the observation. The observation, and then the state will be, the CNN will distill it into some state and takes as input the action and predicts a future value, either an embedding or the observation. Unrolling means that instead of just firing this transition model once, you will take your input, feed it back, your output, feed it back as input, predict again, feed it back as input, predict again, and so on and so forth. So to be able to do that, the output domain should be matching the input domain of this observation. You should be predicting similar things that you feed as input. Yes?
So, the purpose of unrolling and doing multiple steps is that at a time is to learn like a good weighted space representation?
No, that's a good point. The only purpose of unrolling is to look ahead far in the future. You can think about unrolling as our Monte Carlo tree unfolding. Okay, we had a large depth. We wanted to see what's going to happen after 200 steps, 300 steps. That's why we unroll. We cannot use the prediction of our dynamics to tell us what age we should be predicting. If you remember from a previous lecture, we said that if you try to learn this age while you're training your dynamics, you will end up with a trivial solution, which is what? Map every observation to 0, then you will feel 0 prediction error, you will always be predicting 0, so your loss function will not go forward, right? Does this make sense what I'm saying? So that's why to find this age, you need to put some auxiliary tricks. Either what people do is they say this age better be reconstructing the images. You remember this autoencoder coupling that we did? Other people say this age should be coupled with the inverse model. We saw that as well. Other people say this age should predict the rewards as opposed to the observations. Okay? Other people hardwire this age and say, you know what? The only thing I care to predict is motion of my pixels. And this is going to be my age. And I'm going to show you this to you. So this age, other people hardwire it and decide what they care to predict. And there are many, many examples of this. And other people try to learn it through some auxiliary type of loss, not only your prediction loss. Because if you only say, find me an age which I can predict well, then I'll tell you, map every observation to 0. You'll predict it very well. Does this make sense? Yes?
Do we change the action when doing unrolling?
Yes, so in Monte Carlo research, what we did is we say, okay, what if I take this action, where I'm going to end up? Where you end up, again, you sample many actions, and then you query for each of those, again, your model, so you end up in different places. And then where you end up again, you sample actions, and you end up in different places when you unfold the tree. Does this make sense? Now, this is for discrete actions. Once you have continuous actions, doing this search is harder, correct? So we will discuss in a couple of slides that a similar way of searching, once you have a desired, imagine that I give you a desired age goal here, okay? And I tell you, find me the action sequence that will minimize the distance of your prediction in 10 times test from this age goal. You can just backpropagate. You can train it with gradient descent. That's one thing you can do. Other thing you can do is just sampling. Many people do sampling, like state-of-the-art models do sampling. Let me sample actions and see which action takes me closer to age goal. Now you are going to ask, how can I sample efficiently? Well, you can do cross-entropy method. First, you sample coarsely. You see which actions take you closer to the goal. Then you sample finer along those actions, as we had described in previous lectures. Okay, so we have the technical questions to ask, and they're going to come back. But the question is, another question is, if we have a good model, where we're going to use it? Okay, so 3 use cases come in mind for such models. The first is about online planning, okay? Or it's also called model predictive control. You have trained your model, now you are about to take an action. You know what reward you're trying to maximize, you unroll, you try to optimize over your actions, either using discrete sampling or continuous gradient descent, and choose a very, very informative action, okay? And you're done there. There's no policy learning, nothing. Okay, so you learn a model, and I tell you achieve this particular configuration, and then you say, okay, no problem, let me plan or backpropagate through my model, and I'm going to find this desired action. The second case is to use this model to create simulated experience to train your policy. This is the standard name of model-based reinforcement learning. Along with true experience samples, you're using simulated experience samples, so we'll see how this works. And the last case, which was used in AlphaGo Zero, if you remember, we were selecting actions by tree unfolding to be able to suggest very, very smart actions during training. I'm going to show you an example where we trained these neural dynamics and we use something similar to this, and indeed, you explore much better and faster. All right? So the last example I've only seen it so far with ground truth models when we know the model. So now we'll see how we can use this for learning models. Okay? So this is how online planning looks like. We have the state, we sample actions, they take us to different states, we sample actions, we unfold till a desired depth, we evaluate the reward, which end up state takes us closer to our desired configuration, and you choose the action at the initial state, okay? Online planning, we select an action for a particular state we're in. If you remember, this was used in offline, we used this for AlphaGo, you also used it for offline Monte Carlo research for playing Atari games. Is there any question here? Whatever we did before with ground truth models, we do them now using learning-based models. So usually, people, this is usually used with discrete actions, okay? Although I will show you that you can do exactly the same just by discretizing your action space. For continuous actions, you can do gradient descent. This is our well-known computational graph. This is the parameter theta of our policies, our transition dynamics, the states, the policy, action selection, and reward. This is for a non-MDP with known dynamics and known rewards. Now, what do I mean by gradient descent for action selection is the following. Forget about the policy. You just have trained a model here, okay? You have trained this parameter theta. Now you freeze those parameters and you backpropagate. You unfold your model, you unroll your model for a specific number of time steps, let's say 10 time steps. You want to see if your final state is closer to your desired goal. Okay, so you have some differential function there that measures the distance, and then you backpropagate directly towards those actions. You say, what should be my action sequence to give me the desired configuration? Is that clear? Yes, this is the continuous analog of online planning. Because everything is differentiable, we can just take gradient descent directly on the actions. And while you're doing this, of course, your dynamics are frozen. Okay? Now, how we do the second thing, model-based reinforcement learning. You remember this graph. This graph is from stochastic value gradients. I'm sure you remember DDPG, deep deterministic policy gradients. This is going to come up in the homework 3 part 2. The computational graph of DDPG is exactly the same, but there's no Z, there's no stochasticity. But you can make your actions stochastic just by adding this Z, which is sampled from a fixed distribution. You can totally backpropagate through it. Concretely, what happens is in TensorFlow, you sample a bunch of Z's, you push them forward, all of them, compute the gradients, and average. That's it. It's like not much more than what you need to do with deterministic policies. Now, here's again our computational graph of a non-MDP, known rewards, known dynamics, and here's what you can do once you have the dynamics learned, okay, and you're trying to improve your policy. Before, you remember I had removed the policy nodes, we were just backpropagating directly to the actions. Well, here, you can try to maximize your Q function and take gradients directly to change your policy. Okay? This is essentially doing multi-step versions of DDPG. All right? And you can do this because you have the dynamics. All right? In DDPG, you will just using the Q of the particular time step. Does this make sense a little bit? Yes?
When you have visual observation, you need to have the goal image, right?
I think what you're asking is, wait, here, no, here you have a Q function. You don't assume you have the rewards here. Okay, you don't assume you have the rewards. Now, maybe what you're saying is,
In the previous case.
In the previous case, yes, very nice. So we'll discuss about this, yes. Oh, sorry. In the previous case, your question is, how do I compute this reward? Yeah, so what is, I have a final image where I end up, and I have a goal image, which is my desired image configuration, and I take L2 loss, or some loss over some deep features. Another encoding, because this doesn't work, because exactly your frame prediction is pretty bad, is I predicted, for example, motions. It depends. Whatever you predict, your goal should be encoded in the same space. If you're predicting images, your goal should be an image. If you're predicting pixel motions, your goal should be a desired pixel motion. Okay? If your predictions are in terms of some measurements, so for example, how many monsters you killed, and how many lives you have, and how much food you have accumulated, then your goal should be in terms of those quantities. Whatever you're predicting, your goal should be expressed in the same quantities. We will see many different models with different choices for this parameter. And I think this is, but this is an excellent question. Mm-hmm. Yes?
I'm a little confused by why you're using theta in the transition dynamics. So are those thetas the same as the thetas for the policy?
No, I will put a different parameter. They're completely different. I think phi. I had it phi before. Yeah, I agree. That's like, so because usually theta goes with pi, I'm going to put a different parameter there. Okay, efficient exploration. There is no explanation for this. We're just going to see it at the end of the lecture. Now, here are the challenges for model learning. First, errors accumulate during unrolling. We discussed about this. Policy learned on top of a model is upper bounded by the accuracy of the model. That's why, so this is a problem. And the thing is that policies, as soon as your model makes mistakes and thinks that, the reward is closer than what it is, then the policy, if you train a policy on top of those in microdynamics, will definitely exploit this weakness and think that it got there while it didn't. Okay? And the last thing is that with lots of experience, model-free method will always do better. Of course, it means with lots and lots and lots of experience. How do we tackle those challenges? First of all, let me say that this is an open area of research, so I'm just showing you in this lecture what people have done, what decision choices they made, and where we are. This is still open, how you can learn good models and use them to build good policies. But here are some answers. Use the model only to pre-train your policy, and then fine-tune model-free. In this way, you will need much less experience in your model-free fine-tuning than starting from scratch. So that makes a lot of sense, okay? We will not see examples of those answers. These are going to all be seen in the next lecture, okay, when we're going to be talking about local models. Let me show you. But this is a clear fix. Use model not to take gradients, but rather to suggest actions for exploration. This we're going to see at the last example of today's lecture. So try to predict something which is succinct and compact so that you don't have a lot of errors. We'll see an example of Wisdom for this video game where the authors decided to predict some measurements as opposed to some encoding of the observations, and were able to perform the second half by 50% and win the competition, I think last year, the Wisdom competition. And the last, which is barely visible, is to abandon global models, models that are expected to do well everywhere in your state space, and rather train local models, local linear models. These are super fast to fit. Okay, so we will use this in the next lecture, and then do model-based RL using these local models. Very fast you'll be able to achieve your desired action trajectories, and then distill knowledge of those action trajectories, train with those very simple models into complex and expensive neural network policies. Okay, so this is known as guided policy search. You don't train directly your policy, you train cheap model-based learners with very simple local dynamics that work only for this particular initial and final configuration, and then distill those nodes across a neural network to be able to generalize across the state space. Does this make a bit of sense? Again, I'm not sure, I don't believe that it's going to be the final answer to model learning. I'm sure soon, in the future, maybe in 1 or 2 years, we will be able to learn models fast and cheaply. But right now, I think this is where we are, okay? So 3 questions to keep in mind when we discuss about model learning. The first is, what shall we be predicting? And this is very related to the question of your colleague, like, what is the goal in coding? Well, the goal in coding, how you present your goals, depends on what you're predicting. If you want to present your goals as an image, of course you need to predict frames. If you want to present your goal as move the pixels somewhere, then you need to be predicting motions. If you want to present your goal as make noise, then what you should be predicting is the energy in the microphone. Does this make sense? So your prediction should be spanning the space of your goals, ideally. Now, what is the architecture inside here? Yes, of course, you can put a vanilla CNN, but probably it's not going to generalize. People have come up with smart encodings that will try to generalize better across the state space. You have across, for example, you may be learning some model, but there are only 3 entities present, and now there are 6, and you still won't be able to generalize, as opposed to fail miserably. And the last is, what should be the action representation? If the action is very short in time, you are in a bad shape because you need to unroll quite a bit to look ahead far in the future. If your action is a long action trajectory, then potentially you'll need very few unrolls to go far. Okay, so do these 3 questions make sense? Okay, so to motivate all this, we'll start from a very simple case. Let's assume you want to learn to play billiards. All right, there are balls. The agent is allowed to apply a force on those balls directly. There is no stick. You're allowed to apply force on balls. And you want to learn how these balls move under this force of the agent. And once you learn how these balls move, you should be able to play, in the sense that you should have a goal in mind, saying, I want to send this ball to this particular hole, and you should achieve it. Or you want to be seeing a ball moving, and you say, oh, I need to choose the action, so that if I shoot this ball under this action, I apply this force to that particular ball, will hit the moving ball, or any crazy goal you want to come up with, okay? Okay, great. So here is billiards. What are we going to do? Well, when we're about to learn to play billiards ourselves, the first time we went there, first of all, a lot of knowledge carried through by how the objects move in the world. We would never expect to push the ball in that way and the ball to go the other way, for example. So there's already a big amount of transfer, okay? Now, we are tempted to say that models generalize across tasks, right? Model knowledge generalizes. Whatever I have seen from how objects move in the rest of my experience so far, till I reach the billiard table, will be used now. I want to tell you that this is true only if you have the correct architecture for your model. If your model is a big CNN with pixels, I'm not sure that, you've seen a lot of objects, a very different object comes. It's not clear to me that you'll be able to predict the correct motion. It all depends on your architecture. Yes, but model should generalize across tasks. The architectures we need to learn are exactly, would be useful if they're able to generalize across tasks, okay? In any case, you have some prior experience, but then you play and you watch other people playing, and here is how things are going. You apply forces, the balls are moving, and now you want to squeeze now these observations of yours into a neural model that, taking as input the force and how the billiard table looks like, will be able to predict the next billiard table. Okay? Do you think this is a reasonable, let's say, formulation for model learning in this case? What do you think? Here's how it will look like. We'll take the billiard table, we'll take the force, feed them into a CNN, and try to predict the next frame. Okay, if I was only watching billiards played with 5 balls, would I be able to generalize to billiards played with 6 or 7 balls in this case? Potentially no. Potentially my CNN would overfit on these particular numbers of balls where I trained on. All right? Now, that's one problem. The other problem is what your colleague asked. what will my goals be expressed on? Will my goals be, okay, get me this goal image? Or will my goals be, you know, here is the motion of this ball that I want you to achieve, and here is the motion of that other ball that I want you to achieve, and here's the desired location for this ball, etc. It seems to me that in billiards, we think in terms of locations, where we want the objects to be displaced to, okay? This is much more succinct representation, very much fewer numbers than trying to predict the pixels directly. Do you agree with this? So, if we do this change, we are able to predict much better than if we predict pixels directly, okay? So let's put these two ideas now together. So the first idea is instead of fitting to our CNN the full billiard image, the image of the billiard table, we will just focus around a particular object, okay? And we'll learn in this way the dynamics of a particular object in billiards. And then how we'll be able to predict the next configuration of my billiard table? I will apply this model to every object that I have in the scene. So basically, there is again weight sharing. In CNN, there is weight sharing across patches. Here there is also weight sharing, but it's across the objects that I have on the table. Okay? What do you think about this choice? Do you think it's restrictive? Yes.
Since there is only one color, is there a cue board or every board is the same?
Say it one more time. I didn't understand.
Is there a cue board? You can only use one board each time, or what is the field of the force?
Yes. So the force here is applied to the
Only one
center of one ball. Yes.
and you can only choose the same board.
I mean, let's assume I'm a ball that nobody has applied force on. You can still put the predictive model to see where I'm going to end up. Maybe some other ball is going to hit me and I need to move, right? So yes, you can have forces on whatever balls you want, not one ball at a time. Though this is going to be difficult to happen in reality with many people pushing balls at the same time. And this predictive model will apply to every ball, whether there is force on it or not. In fact, forces will be pretty sparse here, right? Most of the time, we just watch balls moving while somebody has already applied the force. Okay? Mm-hmm.
It seems like there could be a problem if two balls interact where sort of the field that you're looking at around the balls don't overlap, right?
Yes. Mm-hmm. Very nice. So your colleague is saying the following. How are we going to coordinate the predictions of displacements for different objects? Here, the choice is, instead of putting a very tiny field of view around each ball, make it big, so that every ball can see its surroundings, and implicitly, when I see that I'm about to collide here, I'll predict this displacement, and this ball sees that I'm about to collide with it, so it's going to predict the opposite displacement, and hopefully, you know, in this way, all predictions will be compatible with each other. Okay, first of all, there shouldn't be people jumping on top of other balls. So this never happens in the 2D world. So our predictive model better also respect this constraint. But the question of your colleague is, sure, but what if there are some, let's say, telepathic interactions between balls that are not in the same field of view, correct? Very nice. So we'll reply to this question in a couple of slides. Okay? Now, it turns out that for billiards, such big receptive field is more than enough because interactions are local. Okay? And in fact, this is also the structural bias that we impose. Because interactions are local, you don't need to look at the full Earth, the whole table at the same time. In the same way as in Earth, you are not going to take the full Earth as input. Probably the way people interact is the same everywhere. So I'm just going to learn the local model and apply it everywhere on Earth. Okay? So this is our first choice. So now this is what the CNN is going to look. It's going to look at the receptive field centered around a particular ball in time. Now our second choice is this. I'm going to be predicting the ball displacement. Okay? Does this make sense? Now your question should be the following. Since we said that to be able to unroll the model forward, we said that our output should match our input. Otherwise, we wouldn't be able to fit it in. Do you agree with this? So if you are predicting displacement, but your input takes images, how they're going to agree with each other? Well, there's going to be a trivial visual renderer that takes the displacement of the balls, pastes them on the table, creates the new image in this way, and then feeds it back in. Okay? So now this may sound like a hack, but it is not. Essentially, it says the following. The world has some certain appearance. When things interact in the world, their appearance don't change. Essentially, motion changes. Okay? The substance, the content, even locally, doesn't change. The same particles are just moving around. So I can just predict only the dynamic part of my world and keep the static part the same. The static part here is the appearance of the balls, for example. Okay? Now, the question is at some point you need to decide what to predict, what to define as dynamic and what to define as static, where the static carries through and you don't need to predict and the dynamic is the fact that you need to predict. So, if you do all these choices, we have an object-centered CNN, we apply to one object at a time, we copy-paste, then you'll be able to match, let's say, the simulator kind of. You see that very fast the predictions look different, but for short term, they look the same. Something that was very important to get this working was hard negative mining. The CNN will learn very, very fast to predict linear motion. But because collisions are very rare, if you don't make sure that you resample them, you sample collisions more than the rest of the data, okay, then the CNN will never learn them, okay? Because does this make sense to you? Okay? And this is always the world. Many dynamics are very easy, and there are some rare events. You really need to replay these rare events enough for your model to learn them. Okay? In fact, this has also a biological explanation. They say once you burn your hand, you touch the stove, you burn your hand, this event replays in your brain quite many times, so the synapses is clear, so you don't need to try again to see if you're going to burn yourself. Okay, so now what I can do, I can see the green ball going up, somebody can tell me, and I can choose actions. I can just sample actions to choose the one that will send the red ball to collide with the green one, for example. Okay? So two good ideas we've seen so far. The first is instead of feeding images, feed graphs. Okay? And the second is to predict motion instead of appearance. And both of those ideas can be carried through in future works, and we'll see these instantiations. Do you have questions so far? Okay. I want to tell you that when this work was developed, we really didn't know if the CNN would learn to bounce back. And I think this is, I mean, people had tried and they were not able to get this working. So now it looks trivial, but back then it was non-trivial. So let's see the three questions that we just answered. So our first question was, what are we predicting? Well, we said we're going to be predicting object displacement trajectories. By the way, whenever we predict something, we will never predict the actual quantity. We will always predict the displacement, the difference of that quantity. So we will never be predicting positions. We're predicting displacements. So the future position will be previous position plus the predicted displacement. Okay? So this is always going to, even if you predict features, you're not going to be predicting the features themselves, but like the delta of the features, which you're going to add in your current features to get your future prediction and feed it back in. So this is always going to be the case. Then we had one CNN per object, which you focus on different objects and you predict the, the future scene. And the last was, our action representation is essentially a force applied to every object. Now the attentive reader will see that there is one assumption here that we made in comparison to a standard frame prediction model. The assumption is that you are able to track the objects that you watch. Because to be able to center your glimpses around these objects, you really need to know where these objects are. Does this make sense? So the claim here is the following. If you really want to predict what's going to happen to an object, it is not possible that you have not detected that object. Otherwise, you wouldn't be asking the question of where this object is going to go in the first place if you cannot even delineate it from its background. Okay? So yes, tracking is absolutely necessary. To start manipulating an object, I should at least be able to see it, if that makes sense. Okay? So visual recognition and detection precedes the desire to manipulate something. All right, so here comes now the question of your colleague. What if the nodes cannot communicate only through the receptive fields? Well, sounds good. Then instead of just considering a bag of nodes, as we did before, we'll also consider edges between them. Now, between every two nodes that you think they are going to communicate, you need to put an edge. This is just a robotic agent. There is no vision here. There is no visual image. I'm just visualizing the robotic agent. And for every joint in that agent, you'll have a node. Every body in that agent is a node. Every link between two bodies is an edge. All right? And we'll learn model dynamics on top of such graph representation. Okay? Now, why this edge is going to help? Well, that's a good question. Well, before we go into details of how we compute the feature updates, let's look at the node features. There are three types of features. One is the observable feature, okay, whatever we can see. And these are 3D positions for the nodes, rotations for the quaternions, linear and angular velocities. Does this make sense? So you can see those features. Then there are some features that you cannot see, like the mass and the inertia tensor. All right? And you can train the model to infer those latent quantities by looking only at dynamic observable trajectories. And the actions are the forces that you applied on the nodes. And here's how the graph update works. We have a graph. The graph is a set of nodes and edges. And every node computes some features. And we've seen this before. Every node, every object had some CNN attached to it and was predicting something. Okay? So here, instead of predicting displacement, you can just predict some features first. Now, all of us are nodes. All of us are predicting some features. And the interesting thing is that we all share the same predicting function, Fn. Does this make sense? And all the edges share the same predicting function, Fe. And why this is important? Because I can be training on graphs with 5 nodes and apply it on graphs on 15 nodes. Okay? So this is important. I don't know beforehand. I mean, now there's no objects in the scene, so it's a bit weird to explain it this way. But the goal is that you train yourself. You train your predictive model with 2 objects. Now 5 objects are there. That's okay. I'm just going to apply the same dynamics and share my weights across the graph. Great, so now we have shared computation between nodes and edges. Everybody has computed some features, and now what's going to happen? Well, every node will send these features to its neighbors. And so then we're not going to have 2 nodes not communicating. I think this answers your question, right? Great. So now we share nodes, and what do? We recompute our features, and we predict the final quantities that we care about. Okay? Does this make sense? That's it. Very simple, in the sense that it comes kind of naturally from the previous setup. And I predict only the dynamic features. I don't predict mass and inertia, etc., because I think these are static. Okay? In the same way that before we predicted positions and we didn't predict the intensity of the balls. Let's go back to our 3 questions. Here, what are we predicting? We predict the dynamic information for those nodes, which means what? Where my body joints are going to be, what is going to be their orientation, what is going to be their velocity and their angular velocity. This is what I'm predicting. Okay? What is the architecture of my model? Where it's a graph neural network, where computation is shared, the weights are shared across edges and across nodes. All right? And there is a lot of recent work about graph neural networks, and we believe it gets a key to generalization, for example, under granularity of your state space. And the last question is your action representation. Well, these are the forces applied to your robotic joints, let's say. Okay? And what can you achieve with this? Well, you can predict very well where your robotic hand is going to end up. And they applied here for different robotic configurations, the swimmer, the runner of the OpenAI gym. And you see that the predictions essentially fall exactly on top of the ground truth. The ground truth is the rollout prediction is the dashed line, and the ground truth is the solid line, and they just fall exactly on top of each other. Okay? So we can predict very well where our agent is going to be. So far, we forget about the environment of the agent. We just want to predict the internal agent state. Does this make sense? Before, I was talking about visual dynamics. Now there are no vision. Okay? I'm just trying to predict, apply force on my robotic hand, and predict its configuration. Okay? And here's what you can do. Well, I can specify for you a full pose, my goal, and then what you're going to do, they're going to run gradient descent, the same we predict in the beginning, estimate what forces you need to apply the joints, and get the robot to match the goal configuration. So again, the important thing to note here is your goal is expressed in the same space as your predictions. Your predictions are in terms of positions, of orientations, and velocities of those. Your goal is also going to be the same. Probably here the velocities are 0, and you just specify the orientation and the position. Yes?
So if you're doing gradient descent, you're solving for the actions, but how do you know how many transitions you would need to take? Or are you doing like a search?
No, you don't do research. Usually you fix your horizon. You say, okay, in 10 steps I want to get to that configuration. You unfold 10 times, you unroll 10 times, and then you backpropagate.
And you just hope that you can actually
Get there.
in that 10 steps.
Yes, if you cannot, then you say, okay, 15. Right? Yeah. I think if you put a large horizon, then if it gets there fast, it's just going to stay.
Oh, okay.
Okay, so that's one good idea that we just saw about going from just objects to a full graph. Now, what about predicting motion instead of appearance? Is this a useful idea, or it was just a hack? Okay. I must say that in the graph CNN we just saw, we were predicting motions, but now I want to say there were no visual dynamics. Now I'm going to show how motion can also be used for predicting visual dynamics. All right? Now for frame prediction, when you want to predict from frame 1 to frame 2, a lot of pixels are the same. What has happened is just the pixels have moved around a little bit. Okay? So instead of training a neural network that takes a sequence of frames and codes them, and decodes them into the next frame, and if you want, you can also put some stochastic units to be able to have some stochastic outputs, like different variations of where exactly the next frame is going to be. Instead of that, you can do a small structural tweak and make this prediction much simpler. Instead of predicting pixels directly, I will be predicting the optical flow, which means, and in fact, the backward optical flow. For every pixel of the resulting image, of the next time-step image I want to predict, I'm going to estimate where from the first image, here, I should be grabbing the pixel from. Does this make sense? Why we're not predicting first of all, let me ask the following question. All people know here what is optical flow? Which people know what is optical flow? Very few. So, whenever we have an image, from one frame to the next, pixels move. This pixel motion field is called optical flow. It's as if the pixel intensities are flowing towards the next image. In computer vision, we have very accurate machinery to predict such motion under small displacements, like when the frame rate is high. Does this make sense? And recently, even this machinery has ended up being a neural network architecture specially designed for this problem. Okay? Now, what I'm saying is that to predict the next frame, instead of just encoding the image into some, compact vector and try to decode it into the next frame, the easier thing would be to predict some motion field and then take the pixels from the previous image and move them. Okay? Now, instead of doing this forward moving, it's like forward warping. The problem with forward warping is that if for every pixel here, you estimate the motion of where it should end up, you're going to end up having holes in that next frame. You're going to end up having locations, pixel locations where nobody ended up there. You don't want that. because then you're going to feed up the images with holes back in your model, and the model is going to be very surprised. So what we do is we compute a backward optical flow. For every pixel here, we say, where should I grab this pixel from in the previous image? And how do you train this neural network? There are two ways you can train it. The first is to encoder, CNN encoder, CNN decoder. Here you predict something that looks like an optical flow, which is what? Two channels as big as the original image, one having the dx and the other having the dy. Okay? So we have 2D motion. And then, so you take this, you don't supervise this, you don't have supervision at all on this motion. Then you do the backward warping, you get the next frame, and then you try to match the pixel intensity there. Okay? That's one way. Now your question should be, but is this warping differentiable? Yes, it is differentiable. This came out of this paper, Spatial Transformers. Essentially, warping is a bilinear sampling. You can totally backpropagate through this bilinear sampling. All right? It's just some weights, essentially. You use for every pixel 4 weights for its neighborhood of how to estimate the intensity. Okay? So now another thing you can do, I must say the following. This loss is very fragile. In the sense that if you have large motions, and imagine I'm here, in the next frame I'm here, however, in the beginning of the training, the flow is what? 0, because all the weights are initialized to 0, so there is nothing here. So I have a very high pixel loss. The neural network doesn't know where to go to pick up the pixel, right? So if you want to do this loss on pixel intensity work, you need to do a multi-scale architecture where in the course of scale it sees that nearby there is something related to me, okay? Otherwise, you can totally estimate this optical flow, okay? And between the next frame and the previous frame, completely unsupervised, using this neural network method that generalizes super well, has trained on synthetic images, and then put the loss based on the flow field directly. And there, once you predict 0, but actually the actual flow is, let's say, 30, then you have a very clear direction where you need to go. And you say, oh, I really need to increase this flow vector from 0 to 30. Do you see that the gradients are much clearer there and you can make faster progress? Okay, so this is an important point, that's why I'm mentioning here. Now, so I'm showing here the tennis player. This has nothing to do with manipulation. So can we use this model for manipulation? This is the question. So here is some predictions. 1, 2, 3 are the input frames. Then you show the optical flow, and then you see the red. First you see the red prediction, and then you see the flow that generated that prediction. Okay? For human motion. Now the question is the following. You have a robot, and there are some objects on the table. Can this robot learn a model of frame prediction which encodes this pixel motion, learns to predict how pixels move under the agent actions, so that if I express my goals in terms of pixel displacements, I say I want this pixel to move from here to here, 10 centimeters to the left, then I can unroll this model forward, look at the final displacements, take a loss, and compute the actions that will get me to that displacement. Do you see what I mean? So again, if we go back to our 3 questions, the first is what are we predicting? We're predicting pixel displacements. You see that pixel prediction is not pixel intensity prediction directly is not used because it doesn't behave well. It doesn't behave well as a goal specification to show an image. Your pixel intensity is so blurred that the pixel matching is really non-uniform. So here we want to predict pixel motions. All right? And we want to express our goals in terms of motions. I want this gun to move to the left. Okay? So that's one thing. The second is what architecture, and the second is the action encoding. So the action encoding is also very interesting in this paper. I think I forgot to put the title of that paper. It's called the self-supervised prediction using temporal skip connections. So I'll add it in a little bit. And the question is the following. Imagine that you have this gripper, and this gripper is moving in front of its background, like this. A robotic agent is moving in front of its background like that. Can you use the model that I just described to predict this motion well. First of all, this model just takes into account the state, which means the visual image. The second thing you need to input is the action, okay? But basically, what this model says is start from the first image, predict optical flow, move the pixels. Now take the second image, move the pixels, predict the third image. Take the third image, move the pixels, predict the fourth image, and so on and so forth. Can we run in our mind what would be the problem with such a predictive model? And let me, to understand the limitation, think about this. I'm here, this is frame 1, and this is frame 2. So now you have trained your model to predict the motion field so that if you are warp frame 1, you'll get frame 2, correct? Now let me show you frame 3. Okay. Now you need to take your prediction, which is frame 2, hopefully it's going to be very close to the real image, and you want to predict frame 3. And again, now you predict frame 3, now you need to predict frame 4 and frame 5. What do you see as the problem? Look, we're in frame 1, this guy is visible. At frame 2, this guy got occluded. Now you're about to predict frame 3, correct? You're only allowed to use pixels of frame 2 somehow. These pixels are gone. You will have an error on this location, all right? And now I occluded all this behind my table. In the frame 4, you're going to have an error in all these locations, and errors will accumulate, and occlusion will just take over. So that's the problem of just using the last frame to predict the future, right? Pixels get occluded. Let's think of some simple fix to this. The beautiful fix that some people wish that was reality would be to go to a 3D space where things are permanent. Okay, not in 2D projections, things get occluded and occluded all the time. You go to a 3D space, things are permanent, and you predict motion of objects in that 3D space. Now, in practice, such 3D lifting has not been accomplished yet, because you need to know camera calibration. Yeah, there are a lot of difficulties in any case going in a learning-based way. What people have done is they try to fit an object model in every object, then you put the 3D mesh in there, then you try to predict motion with the meshes. Now, your 3D mesh doesn't have anything to do with the object that is in the scene, only unless you have designed it to match exactly the object. So it's very model-based, so this has not worked yet, let's say. Okay? Now, does that make sense what I'm saying? Do you understand why occlusion is a problem? Because all the time I'm occluding pixels and you need them to predict the next frame. And as you unroll, I'm going to be occluding. The cumulative occlusion increases so fast. All these will be now gone by the time you reach here. So a very simple fix that the authors proposed was the following. When you're about to predict the next frame, don't just use the last frame. Use all the frame sequence so far. Use, let's say, the last 10 frames. So once I go, this is frame 1 and this is frame 2, and I occluded this guy. That's fine, because to predict frame 3, you are allowed to use this frame where you were seeing this object, okay? So now instead of predicting one transformation, one optical flow from the last frame, you can predict 10 transformations from all your 10 previous images, okay? I think that was very smart. So here are the two competitors. This guy is only looking at the last time step t. Now, he's taking a summation over different transformations, not one that I suggested. Here they have different transformations because each transformation is very simple. It's allowed to have one very simple affine motion, so not a general flow field. But basically, this suffers from occlusions. And this guy, on the contrary, is trying to predict t+1 by using the first and all the frames till then. Okay? All the frames till t. So he's able to grab occlusion portions from previous images. And let me show you the comparison. Well, this is the architecture. Let's see first the comparison. So the first guy is able to see behind the arm. Do you see? While the agent that is able to use the full frame history, while the agent that can only use the last image, look how bad it is. The occlusion, you know, the cumulative occlusion takes over and essentially you cannot predict anything at the end. Okay? Do you think that makes sense to you guys? Now, what is the architecture? The architecture is a bit complicated, but essentially it's convolutions, 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 deconvolutions, deconvolutions. Or you predict a mask because you have different transformations. It's not clear that you need different masks. You can just predict one warping for every image and combine all of them and predict the next frame. Okay? But basically, if you have the differentiable, this spatial transformer module, the rest is extremely easy. Okay? I was hoping that we'll be able to see some of the results here. I want you to see the blur of the predictions. It's a bit slow, that's fine. And here, do you see? So on the left is the agent that only used the last frame, and on the right is the agent that is able to use a history of 10 frames. So as you see, the background is not washed off. Okay, so another thing I wanted to comment about this work is the loss function. The loss function is not exactly what we commented, is not generate the pixel intensity, but rather match the pixel displacements. It's exactly what I said. We estimate the motion and we put it as a loss on the predicted flow field as opposed on the pixels after the warping. Okay, it's way more informative loss function. Let me see if there are other videos here. Oh, here's the object. So we have the initial position and the target position indicated with these dots, and hop, the object is able to push, the robot is able to push in the right direction from the red to green. Okay? Let's see now here what's going to happen. Okay. Okay, so this is, I think, the state of the art on predicting raw visual observations. The question is, do we really need to predict raw visual observations? You see there is blur, and I have an experiment myself with this model to see how much, how much it can generalize and how much occlusion it can take. But I wanted to, in this last part, to think about the following. We do not care to predict our observations. We care to predict, exactly like Tom indicated, some space of rewards. What we care for our actions. Okay, so the monkey was predicting whether it's going to be hungry or when it's going to get the sugar. And what if somebody had told us this and this and this is what you care to predict? And the truth is the following. Sometimes I care about translation, move the object in a particular location. Sometimes I care about rotation, some other times I don't. When I push this off the table, I don't care exactly where it's going to land. Okay? But when I'm trying to grab my phone, I care very much about very subtle motions, right? Because I do it all the time, I need to be extremely fast. So what if somebody had told us what should be this prediction space? What should be this prediction space? So there is this paper, which I like a lot, it's called Learning to Act by Predicting the Future, where the main idea is the following. Somebody has given you some measurement stream. Along with your images, you have these measurements. What are these measurements for this particular game? Well, the measurements will be health, ammunition, levels, and enemies killed for Wisdom, as opposed to one scalar reward. And your goal can be expressed as a combination of those measurements. And here are your prediction targets. As we said, it's always a difference. What is now, what's going to be in the future. Now the thing to notice here is that I'm predicting those measurements for the next Tn frames, Tn time steps. I'm not going to unroll anything. I'm just going to do one shot long-term prediction. Tn was set to, let's say, a number of 32. Okay, so I'm just trying to predict how these measurements change. And the only thing I'm going to do, my goal, G, is going to be expressed as this vector on top of those measurements. So I can have multiple goals. I can say, oh, kill as many enemies as you want, or get as high munition level as you like, or you know, stay healthy and never, you know, diminish your health or something. Does this make sense? So you predict some quantities, and then your goal can be anything in terms of those quantities. So how does this work? It is extremely simple. We just train a neural network predictor that, given the current observation or short sequence of observations, OI, and actions, and goal vectors, given those, it predicts the next measurement differences. Okay? That's all it is. You have a lot of examples. You see, this is N is the number of examples, your experience tuples, and you train with using regression. Now, once you have trained this predictor, how do you choose actions? Using this. You just try to find the action that maximizes this inner product. Okay? There's no policy explicit. You just use the model directly. It's exactly what we said in the beginning, using this gradient descent. You try to find the action so that this is maximized. You don't need an explicit policy. The only thing you train is the model. One question that may come to your mind is, how do I need to collect this data? That would be a good question. You start with a random policy. So you start collecting examples with a random policy. You feed your model. Now you have some basic F. In the beginning, this is going to be completely random. Now you have some basic F. You can estimate your actions, your optimal actions, using this formula. And you should add some exploration noise to have some exploratory behavior to collect more data. Okay, that's how. So we always do this. We always interleave model learning with policy learning. Else, the model that you learn will not be able to capture the state space that the policy is going to send you. So we always have this interleaving. That's exactly what they did. Okay, do you see how simple it is? Now, if you want to see the architecture, it's also extremely simple. You feed the images, the measurements, and the goal, G vector. You encode them, and the only trick that they did is that they predicted for every action the mean of those measurements, and so it's a duplicate, the same mean for every action. And then here, how different actions change this mean. Some increase it, some decrease it. You remember similar thing was when we had this dueling networks, right? And you try to the target F. This is what you're trying to predict. Okay. So that's it. And you do much better than other models that don't consider such measurement screen. For example, the second best method is A3C that use these rewards. They tested their method under different goals. You can train by changing this G vector. How are you going to sample it? Well, you can sample it continuously between an interval between -1 and 1 that tells you how to weight the different measurements, or you can have it fixed during training. And then at test time, if you vary this G vector during training, at test time you can sample a new G vector if you like. They considered 4 environments from the Doom game. Some of them are very easy, some of them are much harder. And the interesting thing, so this is A3C. So in the simple environments, the standard algorithms do well. So now they say it's our approach. You see there's not much difference. Once you go to harder environments, there is a huge, so this navigation is also easy. So let me take you here. So this is A3C. It's killing some masters here. Kind of stuck in the same room. And their approach is just running much faster, right? Because it's a much simpler problem. Now you just have a standard supervised learning problem just to predict those measurements. Now, of course, these measurements better be quite dense in time. If they're very, very sparse, you are not in a good shape. And I think that's the whole point of the measurements. They are not exactly rewards, did you finish the game or not? They give you indicators of how well you're doing. The same way you go to learn to drive, and your teacher is not going to tell you yes, no, it's going to tell you this, you're doing great now. Now, or keep bigger distance, better velocity control, etc. So here is the hardest environment that they created. So you see this is pretty stuck at the same place. This is A3C, and their method is running really fast. That's it. So if we knew what we care to predict, we would just fit it with a standard supervised learning, and then we would optimize for our actions. Okay, very simple. Now we have a very few minutes left. I want to discuss one approach that we recently experimented with, which is the following. Let's assume we want to do continuous control. We very much like this AlphaGo Zero, how it said that it's very important during exploration to choose good actions. So we said, okay, can we do something similar? Can we look ahead during exploration with our learn dynamics? Okay, with our learn dynamics and see if we can choose better actions than, let's say, epsilon grid or some other exploration method. The important choice in this work, you remember these three questions? What is our action representation? What is our architecture? What we're predicting? What we're predicting is the state of the object and the state of the gripper, essentially the 3D location of the object and gripper, and their velocities. Very similar to the graph CNN. So you assume that a visual model already has given you those quantities. The action representation is interesting. We're using Hindsight Experience Replay to learn some basic skills. Reach, transfer, you're holding an object, you transfer it, you reach to a particular location, and you grasp. And each of those skills, if you remember Hindsight Experience Replay, has multiple goals. For example, you can grasp and put this object in many different end locations, or you can reach in very different locations on the table, or you can transfer these objects in very different locations on the 3D. All right? So your action representation is exactly this: which skill and which goal. Now the beauty of this is that once you train those skills, each of those skills becomes a multi-step inverse model. I can specify the skill identity, 1, 2, or 3, and the goal, and issue the policy, and it's going to send me there. Okay? So I can make very big jumps. And then to be able to use those skills to do tree unrolling, on top of the policy that I learned, I need to train dynamics, which means if from this state I issue this skill, 1, 2, or 3, with this goal, what is going to be my resulting state? Where is going to be my gripper, and where is going to be my object? Now, because those skills are so long in time, there are long action trajectories, even 2, 3 unrollings, we're able to look ahead quite many steps. You don't need to do extensive unrolling, and this saves you from error accumulation. All right? So you have a skill set, all right, which is the policy, is the Q function, the dynamics T, U is not important, and at each exploration step, you unfold this tree, you see which tree path got you closer to your goal, because you have your goal expressed in terms of the object 3D centroid, and you pick that action. And the thing is that you don't always trust your model, because then you're going to, if the model is not good, you will never, how to say, recover. But you're stochastic. Sometimes you trust the model, and sometimes you don't, and you just sample from your current policy, for example, your model free. And the interesting thing is to, first, in the beginning, you always trust your model. Right? It's exactly what we said. We say train with model-based, and then fine-tune with model-free. So in the beginning, you trust most of your model, and then at the end, you trust most of the policies, the actions coming of the policy you learned with some epsilon greedy exploration. So using this method, you're able to get much better curves, much accelerated learning over state of the art for complicated skills. We may touch again on this topic of hierarchical reinforcement learning, which means learning some basic skills and then chaining them, compute these computational graphs in time to go far and achieve very complicated longer horizon tasks by composing simpler tasks. What we like here is the following. In this hierarchical reinforcement learning, if you just chain options, you'll end up with something like this. You want to pick up this, and then you'll say, oh, let me go here, let me go down. So basically, you suffer from the modularity of the skills that you chain. While if you just use your skills just to explore and suggest actions, then at the same time you're still training policy over primitive level actions, very simple actions, as opposed to this coarse dynamics, which will end up being very, very suboptimal and doing the things extremely very modular and very awkward. So we do compare against, I think some of your colleagues had asked about skills that had both continuous and discrete actions, and we compare, and exactly we do better because you use the skills to explore, but you don't use the skills to compose your policy over this course. Sub-actions or macro actions. You still allow your policy to be as fast and as expert as it likes to be once you have explored of how to do it. So we have 3 more minutes. I was wondering if we should take some questions now. If you have some questions from this lecture, that's the end. In the next week, we'll discuss about the following. We'll give up on global models, trying to train neural networks that work in all the state space, and we'll focus on what we can do with linear models and trajectory optimization. We'll see how fast they work and what we can do to distill these very simple controllers into big neural network policies afterwards. Are there any questions? Okay, great. So then you're free to go.